Okay, let's make some more generalizations. That was kind of weird how I said that. More generalizations based on what we're learning. Okay, so the data in table 1, boom, represent the probability distribution of the number of people living in households in the U.S. Figure 6, boom, shows a graph of the probability distribution. From the data in table 1, we determine the mean and the standard deviation to be a mean of 2.9 and a standard deviation of 1.48 based on this data. Okay, clearly this is not normal. Clearly, right? So, in fact, the random variable is discrete. Approximate the sampling distribution of the sample mean by obtaining through simulation 1,000 samples of size 4, 10, and 30 from the population, all right? So here is the population. We can see this population's not normal. What is this? It's skewed to the right. Okay, so let's see if my population that I'm looking at is not normal. Now, we're going to use, so in our book, they used a program called Minitab. We're going to use Minitab is the name of the program to run a simulation. To get these histograms. These, oh my gosh, look at that. Too many E's in that word. I have a tendency to go too fast, right? You guys know, you've been with me for a while now. All right, so we're going to use Minitab to run the simulation to get these histograms. So here is our first one, where n is equal to 4. I'm going to scoop this up. So this is where n is equal to 4. And then notice what is happening. We're still skewed right? But is it as much as is it as much as the population? No, do you see that? Still skewed right. But not as much. Right? Where my mean here is, and I don't know if you can see this. No, I don't think you can see that. I have to just pull that out. Where my mean here is the same as my mean. Where did it go? Because the mean is a mean is a mean, right? So here my mean is 2.9, and there's my population standard deviation. Let's use that. Mean is 2.9, but my standard deviation here is going to be that 1.48 divided by the square root of n, and that'll be 0.74, I think. Check my calculations on that. So there's the mean and the standard deviation. Okay, now take a look at what happens whenever n is equal to 10. Still skewed right, but look at what's happening. It's creeping more and more to the middle, isn't it? Still skewed right, but less. Right? My mean is still my mean. What about this standard deviation? 1.48 divided by the square root of 10. Plug that into your calculator. I get 0.47. Is that what you're getting? Okay. Now what happens when n is equal to 30? Yeah, we're starting to see this normal curve, right? This appears to be normal. My mean, still 2.9 because that's where we roll. My standard deviation, 1.48 divided by the square root of 30. Plug that in. What do you get? 0.27, right? Notice what's happening with these standard deviations. They're getting smaller and smaller, right? Closer to the mean. Smaller and smaller standard deviations. This is a much bigger variety because it's skewed more. as we're going down through here. Even more, the 1.48 for the population, right? That's farther away from the mean that we're looking at there. Okay, and look at this n equals 30. That is whenever it starts to appear normal. There's a reason for that. It is called the central limit theorem. The central limit theorem. This says, regardless of the shape of the underlying population, which we just saw, that one that was mega skewed right, and this one is too. Excuse me. The sampling distribution of X bar becomes approximately normal as the sample size increases. That's the key. The sampling distribution becomes approximately normal. Didn't we already talk about this? Maybe something called the law of large numbers? Oh, yes. Yes, we did. Right? Yeah. So that's what's going down here. As we increase, right? As we increase these values, the sample size n increases, then it gets closer and closer to the middle. Look at this one. I don't know if you can see that. That one's 25. It's even still skewed a little bit right. Here's the deal. We have a magic number. If the distribution of the population is unknown or not normal, let me write this down. If the distribution of the population is either unknown or not normal, all right? The distribution of the sample mean, then the distribution of the sample mean is normal provided the sample size is greater than 30. That is the key. So notice what's happening here. Skewed right, skewed right, skewed right. I'm going to go back to that previous one and look what happened. When we hit 30 here, that's when it started to appear normal, when my mean was lined up in the middle. Here, it's called the central limit theorem. As long as your sample size is greater than or equal to 30, then I can treat it like a normal distribution. That's the key to that. If we can call this normal if the sample size is greater than or equal to 30. So if it starts off where it's not normal or it's unknown, no problem. Then we just have to make those sample sizes greater than or equal to 30. And if I know the sample size is greater than or equal to 30, then I can go with the fact that this has been normally distributed. Cool, right? Okay, so look at this example 5. The mean weight gain during pregnancy is 30 pounds with a standard deviation. The mean is 30, the standard deviation of 12.9. Weight gain during pregnancy is skewed right. So automatically they're telling me this is not a normal distribution. So if I know that this is not normal, known that this is not normal, not normal is what I tried to do, then my sample has to be bigger than 30. The obstetrician has a random sample of enough. That's what we're hearing, of enough. This 35 is greater than or equal to 30, so we can treat this as a normal distribution. That's what's happening here, okay? Okay, and determine their mean weight during the pregnancy was 36.2 pounds, all right? So an obstetrician obtains this random sample and determines their mean weight gaining was 36.2. Does that result suggest anything unusual? So here's what we're actually trying to find, right? So I want to say, because this is skewed right, what we're trying to find is the probability that this is greater because it's to the right. So I know that this is greater than that 36.2. That's the probability we're trying to figure out. How is that going? But in order to get a probability, this is based on a sample, right? Sample. So I need to get my mean sample and I need to get my standard deviation sample. That is what we're going for here, right? Okay, this is my data value that I'm trying to determine the probability and how that's going to go down. So the mean is the mean. So my mean here is 30. My standard deviation is going to be the standard deviation of 12.9 divided by the square root of my sample, which is 35 here. Plug that into your handy dandy calculator and give me 4 decimal places. I get 2.1805. Do we agree? So now we have a mean, we have a standard deviation, and what we're trying to figure out is what is this probability, because it's to the right, of 36.2. And we have StatCrunch to do that for us. All right, so we have our mean. I'm just going to type over this one. You know how to get there. We've done it so much. A mean of 30, a standard deviation of 2.1805, and it's to the right, so it's greater than, so that's good so far, 36.2. And there it is, 0.0022. Oops, let me put it all the way over. 0.0022. All right, that's the probability that they're going to weigh more than, they're going to gain more than 36.2 pounds. All right, based on this sample. Now, here's the actual question. Does that result suggest anything unusual? It is unusual. Good, you guys are so good. Look at this probability. What's the criteria for unusual again? Has to be less than 0.05, and that is true, right? Therefore, this is unusual. And now, they like to go through and state it in terms of numbers. So this is unusual because 2 out of 1,000 would have this amount of weight gain. Do you see where we get that 2 out of 1,000? 1,000 has 3 zeros. So if I move this 3 decimal places, that would be 2, right? Because it rounds just to 2. 2 out of 1,000 because 3 decimal places, because 1,000 has 3, right? So that is unusual. And the fact that this is substantially less than 0.05. All right? It's cool, right? Okay, so here's just a little graphic. This little table here just summarizes. We talked about shape, center, and spread, right? So this is how it plays. If the population is normal with the mean and standard deviation, regardless of the sample size, it will be normal. If the population is not normal with a mean and standard deviation, then the sample size as n increases, then it becomes approximately normal. And what does it have to increase? Tell me, what does that n have to be? Greater than or equal to 30. Good. So as it increases, right, even bigger than, but a minimum of 30, and then bigger from there. Then I can use this information. The center is the mean, the spread is my standard deviation, right? Okay, see? Look at this. We're using all this previous information into our current lesson. That makes it so much more fun when we get to use our stuff we already know.